NASA just announced they're spending $20 billion to build a permanent base on the Moon. Not a visit, not a flag-planting mission, a place where humans will actually live. And the engineering behind it is so much stranger than you'd think. The Artemis Base Camp will be humanity's first attempt at calling another world home. But here's what makes this different from every space mission before it. They're not just landing, planting a flag, and leaving. They're building infrastructure, power systems, habitats that can survive temperatures swinging from 250 degrees Fahrenheit in sunlight to minus 250 in shadow. And they're doing it in a place where a single grain of dust can destroy equipment. The location alone reveals how much has changed since Apollo. While those missions landed near the lunar equator for easier access, Artemis is heading to the South Pole. Specifically, the ridge between two craters called Shackleton and de Gerlache. This isn't random. This spot offers something Apollo astronauts could only dream about: near constant sunlight for solar power, direct communication lines to Earth, and most crucially, water ice trapped in permanently shadowed craters just kilometers away. Water on the Moon changes everything. It's not just for drinking. Break it apart and you get hydrogen for fuel and oxygen for breathing. Suddenly, you're not hauling every drop of water and every breath of air from Earth. You're living off the land, or in this case, off the Moon. The timeline is aggressive. Artemis 5 launches in late 2028, carrying the first components of the base. But the real construction begins when they start landing missions every 6 months. Eventually, they're aiming for annual missions, each one adding another piece to the puzzle. By the time they're done, this base will be comparable in size to the International Space Station, but sitting on the surface of another world. Let's talk about what they're actually building. The centerpiece is called the Foundation Surface Habitat. From the ground up, it's a lander stage topped by a metallic element, topped by a 2-story inflatable module. Yes, inflatable. Before you picture a bouncy castle on the Moon, understand that these inflatable structures are more like rigid shells once deployed. They're lighter to transport, larger when expanded, and surprisingly durable. This habitat isn't just a place to sleep. It's self-sufficient in ways that sound almost impossible. It generates its own power, controls its own temperature despite the Moon's extreme swings, shields against radiation that would kill an unprotected human in hours, processes waste, recycles water and air, manages communications, and serves as a science lab, equipment repair shop, and mission control center all at once. The life support system alone is remarkable. It can process urine and condensate back into drinkable water. It reduces CO2 and recovers it for other uses. It generates high-pressure oxygen for both the habitat and the rovers. The system operates at atmospheric pressures of 8.2 pounds per square inch with 34% oxygen concentration, or 10.2 pounds per square inch with 26.5% oxygen, depending on operational needs. For context, Earth's atmosphere at sea level is about 14.7 pounds per square inch, with 21% oxygen. 4 astronauts can live in this habitat for a month at a time. That's the initial plan. As the base expands and systems prove themselves, that duration will stretch to 2 months. Compare that to Apollo missions, where astronauts spent a maximum of 3 days on the surface. and you start to understand the magnitude of what's changing. But one habitat isn't enough. The Italian Space Agency, working through the Artemis Accords, is developing a second module called the Multi-Purpose Habitation Unit. This one has a trick the Foundation habitat doesn't. It can move. Thales Alenia Space is designing it to operate with or without crew aboard, functioning as both an additional living space and a mobile research station. When astronauts need to set up temporary research sites away from the main base, this module goes with them. Now, living quarters are only useful if you can actually get around. That's where the mobility systems come in, and there are two very different approaches being developed simultaneously. The Lunar Terrain Vehicle is essentially a moon dune buggy. It's unpressurized, meaning astronauts drive it while wearing their spacesuits. NASA's specifications are precise. Carry 800 kilograms of cargo, travel 20 kilometers without recharging, operate continuously for 8 hours in a 24-hour period, survive the lunar night when temperatures plummet, and handle slopes up to 20 degrees. 3 companies are currently competing to build this vehicle: Intuitive Machines, Lunar Outpost, and Venturi Astrolab. Each has a different design philosophy, but here's what's unusual about this contract. NASA isn't buying the rovers, they're renting them. The companies will own and operate the vehicles, and NASA pays for the service. It's the same model that revolutionized cargo delivery to the International Space Station, now applied to lunar exploration. The second mobility system is far more ambitious. The pressurized rover is basically a lunar RV. Astronauts can drive it in regular clothes, not spacesuits. It has its own life support systems, sleeping quarters, and enough supplies for trips lasting weeks. This vehicle will let crews venture tens of kilometers from the base, exploring regions that would be impossible to reach otherwise. Think of it this way. The Lunar Terrain Vehicle is for daily commutes around the base. The pressurized rover is for road trips into unexplored territory. One extends the range of a single work shift. The other enables multi-week expeditions into the unknown. Getting all this equipment to the moon requires solving a problem that doesn't exist on Earth. There's no atmosphere to slow you down. Every landing is powered. Every descent burns fuel. That's where the human landing systems come in, and NASA is developing 2 different vehicles simultaneously. SpaceX's Starship HLS stands about 165 feet tall, roughly the height of a 15-story building. It launches on a Starship booster, reaches Earth orbit, then gets refueled by multiple tanker spacecraft. Only after refueling does it boost toward the moon, enter a near rectilinear halo orbit, and wait for its crew to arrive separately on an Orion capsule. An elevator transports astronauts and cargo between the lander and the lunar surface. Blue Origin's Blue Moon takes a different approach. It's smaller, designed to carry 2 astronauts to the surface for stays up to 30 days. The first uncrewed demonstration is scheduled for 2027, with the first crewed mission on Artemis 5 in 2030. Both systems are being designed from the start with cargo variants in mind, because delivering habitats, rovers, and construction equipment requires far more capacity than just landing astronauts. But none of this works without power. The South Pole location helps because the sun hovers near the horizon almost constantly, providing consistent solar energy. Almost constantly isn't the same as always, though. There's no single location at the South Pole that never experiences darkness. Some sites go dark for up to 8 days at a time. Solar panels can handle short gaps. NASA is designing battery systems that can keep critical systems running through those dark periods. But for longer-term operations, for a base that needs to function year-round regardless of sunlight availability, solar power alone won't cut it. That's why NASA is developing a nuclear fission reactor specifically for the Moon. The initial design goals are modest by nuclear standards: produce 10 kilowatts continuously, weigh less than 6 metric tons, and operate for at least 10 years without maintenance. 10 kilowatts is roughly the average annual power consumption of a home on Earth, enough to keep the base running, recharge rovers, power life support systems, and enable scientific research. 3 companies received $5 million contracts in 2022 to develop competing designs. Each had to include not just the reactor core, but the power conversion systems, heat rejection systems, and power distribution networks. The designs also had to account for cost and provide realistic development schedules. The next phase is more ambitious. Current plans call for a fission reactor that produces at least 100 kilowatts of electrical power, plus waste heat that can be used for thermal management. That's enough to power a serious industrial operation, enough to support not just life support and research, but manufacturing and construction. A nuclear reactor has advantages beyond just power output. It can operate in permanently shadowed regions where solar panels are useless. It provides power continuously through the 14.5-day lunar night, and it enables NASA to place the base optimally for resources and science, rather than being constrained by sunlight availability. But deploying a nuclear reactor on the Moon presents challenges that don't exist on Earth. You need a landing pad capable of handling the repeated rocket exhaust from landing and takeoff. Until that pad is built, NASA is considering creative solutions, positioning the reactor behind large boulders for blast protection, or using natural topography as shielding. The pad itself becomes a construction project. You can't just pour concrete on the Moon. Instead, NASA is developing techniques to use lunar regolith, the dusty soil covering the surface, as a construction material. High-powered lasers can melt regolith, which then solidifies into a ceramic-like material strong enough to serve as a landing pad. This is where in-situ resource utilization starts to become critical. ISRU is the practice of using local materials instead of hauling everything from Earth. On the Moon, that means using regolith for construction, extracting oxygen from lunar soil, and processing water ice into fuel and life support supplies. The mass savings are staggering. Water weighs about 8 pounds per gallon. Launching it to the Moon costs roughly $10,000 per pound. If you can extract water locally instead of shipping it, you've just saved $80,000 per gallon. Scale that up to the thousands of gallons needed for a permanent base, and local resource extraction becomes not just helpful, but essential. NASA's Kennedy Space Center has been developing 3D printing systems that use regolith mixed with polymer binders. The Icon company is working on laser-based systems that melt pure regolith without binders. Both approaches have been tested in simulated lunar conditions. Temperatures around -200 degrees Celsius, vacuum conditions around 10 to the -3 torr. The results are promising. Test structures printed in these conditions show strength comparable to concrete. They can withstand micrometeorite impacts, resist radiation, and handle the extreme temperature cycles that would destroy conventional building materials. This matters because the Moon is hostile in ways Earth isn't. There's no atmosphere to burn up incoming debris. Micrometeoroids hit the surface at orbital velocities, carrying enough energy to puncture thin metal. NASA calculated that a base the size of the International Space Station at the South Pole would experience about 15,000 micrometeorite impacts per year. Fortunately, 99.9997% of those impacts are too small to penetrate current shielding technology. The remaining 0.0003% that could penetrate translates to one potentially dangerous strike every 42 years. Not zero risk, but manageable with proper design. Radiation is the other major threat. Earth's magnetic field and atmosphere shield us from most cosmic radiation. The Moon has neither. Astronauts on the surface will be exposed to radiation levels roughly 200 times higher than on Earth. Over the course of a month-long stay, that exposure approaches the annual limit for radiation workers on Earth. The solution involves multiple strategies. The habitats use water-filled walls that absorb radiation while serving as water storage. Regolith can be piled against exterior walls, using the lunar soil itself as shielding. The base design places sleeping quarters in the most heavily shielded areas, reducing exposure during the 8 hours per day when astronauts aren't actively working. All of this construction requires getting materials to the surface, and that's where the Commercial Lunar Payload Services program becomes crucial. CLPS missions started in 2024, using commercial landers to deliver scientific instruments and equipment. These missions will continue throughout Artemis, delivering base modules, rovers, construction equipment, and supplies. The logistics are complex. Each mission must be carefully coordinated. You need the power systems in place before you can operate the habitats. You need landing pads before you can safely deliver the heavy equipment. You need resource extraction systems operational before you can reduce resupply requirements from Earth. The sequence matters, and getting it wrong means delays measured in years, not weeks. That sequential challenge shapes the entire mission architecture. Artemis 4, targeted for 2028, will deliver the first landing since Apollo. But before astronauts set foot on the surface, cargo missions will have already placed critical infrastructure. The HLS vehicles themselves become part of that infrastructure. SpaceX's Starship HLS stands about 165 feet tall, roughly equivalent to a 15-story building. Blue Origin's Blue Moon will be smaller but equally capable, designed to support 2 astronauts for up to 30 days starting with Artemis 5 in 2030. Here's what makes these landers different from Apollo's lunar module. The Apollo LM was disposable, used once and abandoned. Starship HLS and Blue Moon are designed for reusability. They'll remain in lunar orbit between missions, ready for the next crew. That reusability changes the economics entirely. Instead of building a new lander for every mission, you're amortizing the cost across multiple flights. The savings compound over time, but getting these massive vehicles to lunar orbit requires a logistical ballet that makes Apollo look simple. Starship HLS launches on a Starship booster, enters Earth orbit, then waits. Multiple tanker starships launch afterward, each carrying propellant. They rendezvous with the HLS version, transferring fuel in a series of orbital refueling operations. Current plans call for roughly 10 to 15 refueling flights per HLS mission. Only after those refuelings is the HLS vehicle capable of boosting itself to lunar orbit. That's a lot of launches. Each one carries risk. Weather delays, technical issues, orbital mechanics constraints. Any of these can cascade into schedule slips measured in weeks, and you can't just park a partially fueled Starship in orbit indefinitely. Propellant boils off over time, especially the super cold liquid oxygen and methane that Starship uses. The entire refueling sequence needs to happen within a relatively tight window. Blue Moon faces different challenges. It launches on New Glenn, Blue Origin's heavy lift rocket, which hasn't flown yet as of early 2026. The lander uses liquid hydrogen and liquid oxygen, propellants with their own storage complications. Hydrogen is notoriously difficult to handle. Its molecules are small enough to leak through materials that would contain other gases. Long-term storage in space requires active cooling systems to prevent boil-off. Neither company has attempted anything like this before. SpaceX has never refueled a vehicle in orbit. Blue Origin has never sent hardware beyond Earth orbit. NASA's betting on both approaches working, which provides redundancy but doubles the technical risk. If one system fails, the other might still succeed. If both encounter problems, the entire timeline collapses. The mission sequence assumes everything works. Artemis 4 lands near the South Pole, probably somewhere in the Shackleton-de Gerlache area. The crew spends about a week on the surface, conducting EVAs, testing equipment, scouting locations for future infrastructure. They're not building anything permanent yet. This is reconnaissance, validation, that the chosen site actually matches the remote sensing data. Artemis 5, scheduled for late 2028, is when construction begins. This mission carries the Foundation surface habitat, the core structure that will become home for future crews. The habitat design is fascinating in its complexity. From top to bottom, a two-story inflatable element that provides living space, a one-story metallic element that houses critical systems, and a lander stage that serves as the foundation. That inflatable element solves a fundamental problem. You can't launch a fully expanded habitat. It wouldn't fit inside any rocket fairing. But you can launch a compressed structure that inflates after deployment. NASA's been testing inflatable modules on the International Space Station since 2016. The beam module has exceeded all expectations, proving that fabric structures reinforced with Kevlar-like materials can withstand the space environment for years. The lunar habitat takes that concept further. The inflatable section provides roughly 400 cubic meters of pressurized volume, enough space for 4 astronauts to live and work for a month without feeling like they're in a submarine. Compare that to Apollo's lunar module, which gave 2 astronauts about 6.7 cubic meters of habitable space. You couldn't stand up fully. You couldn't move around. This is different. This is a place you could actually live. The metallic section below handles the heavy engineering, environmental control and life support systems that recycle air and water, power management and distribution, thermal control to handle temperature swings from -170 degrees Celsius in shadow to +130 degrees Celsius in sunlight. Communication systems for constant contact with Earth. Radiation shielding using water-filled walls that double as water storage. Waste processing equipment. Airlock interfaces for EVA operations. All of this equipment needs to work autonomously before crew arrives. The habitat will sit on the lunar surface for weeks or months, operating remotely, proving its systems before anyone moves in. This is where that early power infrastructure becomes critical. Solar arrays deployed by previous missions will already be generating electricity. Cables will connect them to the habitat site. Everything gets tested, validated, debugged, without crew in the loop. The testing phase reveals something important about NASA's approach to risk. Apollo accepted risks that would be unthinkable today. The LM's descent engine had never been tested in a full-duration lunar landing profile before Apollo 11. Armstrong and Aldrin were test pilots in the truest sense. Modern missions can't operate that way. Political support evaporates if astronauts die. Public opinion shifts. Funding disappears. So everything gets tested exhaustively before crew commits. That caution adds time, but removes catastrophic failure modes. When crew arrives at the habitat during Artemis 5, they're moving into a structure that's already proven it can maintain pressure, regulate temperature, recycle air and water, communicate with Earth, and survive the lunar environment. The unknowns are reduced, though never eliminated. Space doesn't forgive mistakes. Inside the habitat, life support systems operate at pressures lower than Earth normal. The current design calls for 8.2 pounds per square inch with 34% oxygen concentration, or alternatively 10.2 pounds per square inch with 26.5% oxygen. Compare that to Earth's 14.7 pounds per square inch with 21% oxygen. Lower pressure reduces structural stress on the habitat walls. Higher oxygen percentage compensates for the lower pressure, ensuring astronauts get enough oxygen with each breath. This matters for EVA operations. The spacesuits will operate at even lower pressure, probably around 4.3 pounds per square inch. Going from 14.7 pounds per square inch directly to 4.3 pounds per square inch would cause decompression sickness, the same condition that affects scuba divers who surface too quickly. But going from 8.2 pounds per square inch to 4.3 pounds per square inch is manageable with proper pre-breathing protocols. Astronauts breathe pure oxygen for a period before the EVA, purging nitrogen from their bloodstream. The reduced cabin pressure makes this pre-breathing shorter, saving time on EVA days. The suits themselves represent a complete redesign. Axiom Space won the contract to develop the Axiom Extravehicular Mobility Unit, building on NASA's prototype work, but incorporating modern materials and manufacturing techniques. The AXIOMU is designed to fit at least 90% of the US population, male and female. Apollo suits were custom-made for specific individuals. ISS suits come in a limited range of sizes that don't fit everyone. This is the first suit designed from the start for true size flexibility. Mobility is the key improvement. Apollo suits were stiff. Bending at the waist took effort. Kneeling was nearly impossible. Picking up a rock from the ground required astronauts to devise elaborate techniques because they couldn't bend down normally. The AXIOMU uses bearing joints at shoulders, hips, knees and ankles that allow natural movement. Astronauts can kneel, crouch, reach overhead, and manipulate tools with fine motor control that wasn't possible in earlier designs. They'll need that dexterity because the work ahead is complex. While the Foundation surface habitat provides the core living space, it's only the beginning. The Italian Space Agency contracted with Thales Alenia Space in late 2023 for a multi-purpose habitation module that may become the second habitat element. This module is designed to operate with or without crew present and has the ability to move on the surface, though the mechanism for that movement hasn't been fully revealed. Adding modules expands capacity. 4 astronauts in one habitat is manageable for a month. 8 astronauts in 2 connected habitats could stay longer, accomplish more science, build more infrastructure. The expansion follows ISS principles. Start with a core module, add pieces over time, create a complex that grows with the program's needs. But expansion requires mobility systems to transport materials between locations. That's where the Lunar Terrain Vehicle comes in. NASA's specified requirements are precise: 800 kilograms of cargo capacity, 20-kilometer range on a single battery charge, 8 hours of continuous operation in a 24-hour period, survival through the lunar night, and ability to handle slopes up to 20 degrees. Those specs sound modest until you consider the environment. 20 kilometers on the Moon isn't the same as 20 kilometers on Earth. Lunar soil is abrasive, clinging to everything, working its way into mechanical joints. Temperature extremes stress materials. There's no air for convective cooling, so heat management becomes entirely dependent on radiation. And the lunar night lasts 14 Earth days, during which temperatures plummet to -170 Celsius. Any vehicle that survives that without active heating is a materials science triumph. NASA's not buying these rovers. They're contracting them as a service. Intuitive Machines, Lunar Outpost, and Venturi Astrolab are all developing competing designs in a 12-month feasibility phase. The winning design will be operated by the company, with NASA paying per kilometer or per mission. This approach shifts maintenance responsibility to the contractor while giving NASA flexibility to scale usage up or down based on needs. The unpressurized LTV handles local transport, but longer expeditions require the pressurized rover, essentially a mobile habitat that lets astronauts travel for weeks at a time without returning to base. This vehicle provides full life support, sleeping quarters, and workspace while covering distances measured in tens of kilometers. It's less capable than the main habitat, but more capable than the LTV, filling the gap between day trips and permanent residence. That 3-tier approach mirrors how we explore on Earth. You have a home base, a daily use vehicle for nearby work, and an expedition vehicle for extended journeys. The difference is that on the Moon, your expedition vehicle needs to keep you alive in an environment that's actively trying to kill you. No atmosphere means no weather, but it also means no protection from radiation or micrometeorites. Temperature management becomes the responsibility of active thermal control systems. Water recycling can't fail. Power systems need redundancy. The pressurized rover concept pushes current technology to its limits. Battery energy density determines range. Life support reliability determines how long crew can stay away from base. Radiation shielding adds mass, which reduces range. Every design decision involves trade-offs between capability, safety, and feasibility. These vehicles won't exist in isolation. They're part of an integrated surface infrastructure that includes power systems, communication networks, navigation beacons, and eventually resource processing equipment. That integration is where the real complexity emerges, because everything has to work together, and everything arrives on different missions spread across years. Power changes everything. You can have the most sophisticated habitat design ever conceived, rovers capable of traversing any terrain, and landing systems that deliver tons of equipment with precision. But without continuous, reliable power, you have expensive metal boxes sitting in the dark, slowly freezing to temperatures that make liquid nitrogen look warm. That's the fundamental challenge NASA's solving right now. The moon base needs power systems that work through conditions no terrestrial infrastructure has ever faced. Solar panels that function when the sun barely clears the horizon. Batteries that survive temperature swings of 300 degrees. And eventually, a nuclear reactor small enough to fit on a lander but powerful enough to run an entire outpost. Let's start with what seems simple. Sunlight. The South Pole location was chosen partly because the sun never fully sets there. It hovers near the horizon continuously, providing what appears to be an endless power source. Except it's not that straightforward. Imagine trying to run your home on solar panels positioned to catch sunrise light permanently. The sun's at a low angle, meaning less energy per square meter. Shadows from nearby ridges and crater rims create dark zones. And while there's no single location that experiences total darkness, there's also no location that receives constant illumination either. NASA's baseline assumption requires systems to survive 8 days without power. 8 days in lunar night means 8 days at temperatures dropping to -170 Celsius. Most electronics don't just stop working at those temperatures. They suffer permanent damage. Batteries lose capacity. Lubricants freeze solid. Materials contract, creating gaps where seals should be. The engineering response involves thermal mass and insulation. You essentially build battery systems inside insulated containers with enough thermal capacity to maintain operational temperatures through the dark periods. This adds mass, it adds complexity, and it means your power storage system needs to store enough energy not just to run the base, but to keep itself warm enough to function. Solar arrays at the South Pole need different designs than equatorial systems. They mount vertically or at steep angles to catch low-angle sunlight. They track the sun's movement along the horizon rather than across the sky. And they need redundancy because lunar dust accumulation is a slow but persistent problem with no atmosphere to blow it away. That's why NASA's developing nuclear power for sustained operations. The Fission Surface Power Project is designing reactors that change the entire equation. 10 kilowatts of continuous power, equivalent to an average American home, running day and night regardless of sun position. Think about what that enables. Life support systems that never enter low power mode. Rovers that charge whenever they return to base. Communications that don't depend on battery reserves. Science instruments that run continuously. And most critically, water extraction and processing systems that operate around the clock. The reactor specifications tell you everything about the constraints. Under 6 metric tons total mass, 40 kilowatts electrical output, 10-year operational lifetime. Those numbers aren't arbitrary. They're derived from launch vehicle capacity, power requirements analysis, and mission duration planning. 6 metric tons sounds heavy until you realize it includes the reactor core, power conversion systems, heat rejection radiators, shielding, and control systems. That's an entire power plant compressed into something you could fit in a large shipping container. The 40 kilowatt output provides margin. Base systems might need 10 kilowatts for life support and communications, leaving 30 kilowatts for charging rovers, running science equipment, and eventually powering ISRU systems that extract water and oxygen from lunar regolith. But here's where it gets interesting. You can't just land a nuclear reactor next to your habitat and flip a switch. The reactor needs its own landing pad, a prepared surface that won't kick up debris during landings and won't contaminate the reactor with dust, which means early missions need to prepare that site using solar power and battery systems. It's a bootstrapping problem. You need power to build the infrastructure that supports the power system that enables everything else. NASA's solution involves phased deployment. Early missions bring solar arrays and battery systems sufficient for initial operations. Crew prepare the reactor site. A dedicated cargo mission delivers the reactor. Subsequent crew activate it and transition base power from solar to nuclear. The timeline matters because reactor development, testing, and certification takes years. Current plans target a surface demonstration by 2030, which means the reactor flies after initial habitat deployment. But before the base expands to permanent occupancy, heat rejection presents its own challenge. On Earth, power plants use cooling towers, rivers, or ocean water to dump waste heat. The Moon has none of those options. No convection means no air cooling. No water means no evaporative cooling. Everything depends on thermal radiation. The reactor design includes radiator panels that glow dull red in infrared, radiating heat directly to space. Those radiators need protection from micrometeorite impacts while maintaining clear views of the sky. They need to handle thermal cycling as the sun moves. And they need fail-safe geometry so that even if some panels fail, the reactor can still cool itself safely. Placement becomes critical. The reactor needs to be close enough to base infrastructure that power transmission losses stay manageable, but far enough away that any malfunction doesn't threaten crew. It needs to be positioned so its radiators don't face the habitat, avoiding thermal radiation that could interfere with habitat cooling systems. And here's something most people don't consider. The reactor needs a clear line of sight to Earth for telemetry and remote monitoring. If something goes wrong, engineers on Earth need real-time data to diagnose the problem and guide crew through response procedures. The power distribution network connects everything together. Underground cables protected from thermal cycling and micrometeorite impacts. Junction boxes at each major facility. Redundant power buses so that failures don't cascade. Voltage regulation systems that handle varying loads as rovers charge, life support cycles, and science instruments activate. That infrastructure doesn't exist initially. Early missions run on portable power systems, essentially sophisticated battery packs that crew move between work sites. As the base grows, permanent power distribution gets installed. Cables get buried in lunar regolith for thermal stability and protection. Junction boxes get mounted on permanent structures. This is where ISRU starts changing the equation. Once you can extract water from lunar regolith, you can electrolyze it into hydrogen and oxygen. Oxygen supports life support systems, but both hydrogen and oxygen enable fuel cell power generation, a backup power source independent of both solar and nuclear systems. The chemistry's straightforward. Combine hydrogen and oxygen in a fuel cell, generate electricity and water. The water gets recycled. The process is reversible. When you have excess power from solar or nuclear sources, you can run electrolysis to produce hydrogen and oxygen, essentially storing energy in chemical form. Fuel cells provide peak power for high-demand operations, When a cargo lander approaches, power-hungry guidance systems activate. When multiple rovers need simultaneous charging, fuel cells supplement reactor output. When science instruments run high-power experiments, fuel cells handle the load spike. This creates a three-tier power architecture. Nuclear provides baseline continuous power, solar supplements during illuminated periods, and fuel cells handle peak demands. Each tier backs up the others. Lose the reactor, and solar plus fuel cells maintain essential operations. Lose solar, and reactor plus fuel cells continue. Lose fuel cell capacity, and reactor plus solar keep critical systems running. But you need water to make fuel cells work, which brings us back to ISRU. The South Pole location was chosen partly for water ice deposits in permanently shadowed craters. That ice represents stored hydrogen and oxygen, fuel and oxidizer, life support and power storage, all locked in frozen form beneath the surface. Extracting that water requires power. Heating regolith to release water vapor. Running pumps to collect vapor. Purifying water to remove contaminants. It's an energy-intensive process that only makes sense once nuclear power comes online. The timeline synchronizes across systems. Habitat arrives first, operating on solar and batteries. Crew establish base operations. Reactor arrives and comes online. Water extraction begins. Fuel cell infrastructure deploys. Within a few mission cycles, the base transitions from Earth-dependent consumables to increasingly local resource utilization. Every kilowatt generated on the Moon is a kilogram you don't launch from Earth. Every liter of water extracted locally is a liter you don't ship 400,000 kilometers. The economics of lunar presence depend entirely on making power and resources locally available. That's why power systems aren't just enabling infrastructure. They're the critical path for everything else. Without reliable power, you're running camping trips. With it, you're building a settlement. The reactor design reflects lessons from terrestrial systems while adapting to lunar constraints. Passive safety features ensure that even complete failure of control systems results in safe shutdown. The reactor can't melt down because its design makes criticality impossible above operating temperature. Lose cooling, and the reactor shuts itself down through thermal expansion of core materials. Those safety features add mass and reduce efficiency, but they're non-negotiable for a system operating 400,000 kilometers from any repair facility. The reactor needs to be inspector-proof, safe enough that crew can work nearby without constant monitoring, reliable enough that it operates autonomously for months between maintenance periods. Power storage complements generation. Battery systems sized for 8-day survival periods represent enormous energy storage by terrestrial standards. Those batteries need thermal management, charge controllers, and monitoring systems. They need to cycle repeatedly without degradation. And they need to operate in vacuum, where conventional battery cooling doesn't work. NASA's testing lithium-ion batteries in lunar conditions, evaluating degradation rates under thermal cycling and radiation exposure. The data determines replacement schedules, how often battery modules need swapping before capacity fades below acceptable levels. Power enables everything that follows. Communication systems transmitting data to Earth, life support maintaining atmosphere, thermal control managing temperature, science instruments analyzing samples, manufacturing equipment processing regolith, construction robots assembling structures. Each system draws power continuously. Each system needs redundancy. And each system contributes to the total power budget that determines whether base operations stay within available generation capacity. That budget grows with every expansion. Add a second habitat module, and power demand increases. Deploy additional rovers, and charging requirements rise. Install larger science instruments, and baseline load climbs. The power system needs to scale with base growth. Adding generation capacity before demand exceeds supply, which means planning power infrastructure years before you need it. Reactor sites prepared during early missions. Fuel cell components delivered before water extraction begins. Solar arrays positioned for future expansion. The power grid designed with growth in mind, not just current needs. This is infrastructure in its purest form. Investment in systems that enable everything else, that pay dividends across every subsequent operation, that transform what's possible on the lunar surface. Now consider what happens when you need to move across that surface. Mobility transforms access. The base sits in one location, but science targets scatter across kilometers of terrain. Permanently shadowed craters hold water ice. Sunlit ridges offer solar power. Geological features requiring investigation spread across the South Pole region. Walking limits range to a few hundred meters from the habitat. You need vehicles. The Lunar Terrain Vehicle solves near-base transportation. Think utility truck, not Mars rover. It's unpressurized. Astronauts ride in suits, exposed to vacuum, but it carries 800 kilograms of cargo, traverses 20 kilometers without recharging, operates for 8 continuous hours. It handles slopes up to 20 degrees, navigates boulder fields, crosses rough terrain that would stop wheeled robots. NASA isn't buying these vehicles, they're contracting mobility as a service. 3 companies, Intuitive Machines, Lunar Outpost, Venturi Astrolab, are developing competing designs during a feasibility phase. The winner delivers rovers that NASA rents per mission. This shifts development risk and cost to commercial partners, while ensuring vehicles incorporate the latest technology without lengthy government procurement cycles. The LTV needs autonomous capability. When crew aren't present, it operates remotely or independently. Positioning equipment before crew arrival, retrieving samples from hazardous locations, conducting survey traverses. The vehicle becomes a robotic asset between crewed missions, extending operational tempo beyond human presence. Battery technology determines range. 20 kilometers represents significant distance on foot, but modest range for a vehicle. The constraint isn't motor efficiency. It's energy storage in lunar thermal extremes. Batteries that work at -200 Celsius require specialized chemistry and thermal management. They need to survive 2-week lunar nights when temperatures plummet, then operate immediately when sun returns. Charging infrastructure matters as much as the rover itself. Solar arrays at the base provide power, but what about field operations? Extended traverses require portable charging or battery swaps. Mission planning becomes an energy budget problem. How far can you travel on available power while maintaining safety margins for return? Communication range creates operational limits. The LTV needs continuous contact with base or Earth for safety monitoring. Lunar terrain blocks line-of-sight signals. Hills, crater walls, and ridges create dead zones where communication drops. Navigation systems need to function without GPS. The Moon has no global positioning satellites. Rovers rely on inertial guidance. visual odometry, and landmark recognition. The pressurized rover operates on entirely different scales. This is a mobile habitat, not a utility vehicle. 2 to 4 astronauts inside, wearing regular clothes, living for weeks away from base. It's the difference between a work truck and an RV. One extends daily operations, the other enables expeditions. Pressurization changes everything about vehicle design. The cabin maintains 1 atmosphere against vacuum outside. That pressure differential creates structural loads across every seal, hatch, and window. The vehicle needs life support systems comparable to the habitat module: oxygen generation, CO2 scrubbing, humidity control, temperature regulation. It needs water storage, waste management, food preparation facilities. It becomes a self-contained survival system on wheels. Range extends to hundreds of kilometers. Multi-week expeditions explore regions far beyond base camp reach. Permanently shadowed craters that might hold billions of tons of water ice. Ancient volcanic features revealing lunar geological history. Impact sites containing material from deep within the Moon's interior. The pressurized rover makes these locations accessible without building multiple bases. But long-range mobility introduces risk factors that don't exist near base. Your days of travel from safety. Mechanical failures become emergencies. Medical issues can't wait for evacuation. The rover needs redundancy in critical systems. If primary life support fails, backups maintain crew survival until rescue. If mobility systems break, crew can survive in place while awaiting recovery. Navigation becomes expedition planning. Unlike the LTV's daily sorties, pressurized rover missions require detailed route mapping, identifying safe paths through rough terrain, locating charging or camping sites with acceptable solar exposure, calculating energy budgets for multi-day traverses, ensuring communication coverage through relay satellites or line of sight to Earth. The rover carries science equipment that wouldn't fit on the LTV. Drilling rigs for subsurface sampling, ground-penetrating radar for mapping ice deposits, spectrometers for compositional analysis. The vehicle becomes a mobile laboratory, conducting investigations at each stop along extended traverses. Data collected far from base expands scientific return beyond what habitat-bound operations could achieve. Maintenance requirements differ between vehicle types. The LTV returns to base after each mission for inspection and service. Technicians check battery health, examine wheel wear, update software. The pressurized rover might operate for weeks between maintenance cycles. It needs built-in diagnostic systems that monitor component health and predict failures before they occur. Both vehicles face lunar dust as their primary environmental threat. Regolith particles are microscopic, electrostatically charged, and incredibly abrasive. They infiltrate seals, coat surfaces, damage mechanisms. Apollo astronauts found dust management nearly impossible. It covered everything within hours. Modern rovers need dust mitigation strategies that Apollo lacked. Magnetic seals, electrostatic repulsion, sealed bearing assemblies. Dust affects mobility through multiple mechanisms. It coats solar panels, reducing power generation. It accumulates in wheel assemblies, increasing friction and wear. It contaminates cabin air systems if it penetrates pressure seals. Every surface exposed to regolith needs either dust-resistant design or regular cleaning procedures. Thermal management challenges both vehicle types differently. The unpressurized LTV exposes all systems to extreme temperature swings. -200 to +120 Celsius between shade and sun. Electronics need individual thermal protection. The pressurized rover maintains internal temperature through active systems, but that requires continuous power consumption. During lunar night, keeping the cabin warm enough for crew survival drains batteries that might otherwise extend range. Radiation shielding becomes critical for long-duration rover missions. The habitat provides substantial radiation protection through regolith shielding and material mass. The pressurized rover has minimal shielding. Its mass budget prioritizes mobility over protection. Crew accumulate radiation dose during expeditions that must be tracked against mission limits. Extended traverses might require scheduling around solar activity to avoid radiation storms. Vehicle recovery procedures need planning before missions launch. If a pressurized rover fails far from base, how do you rescue the crew? Another rover could retrieve them, but that requires having a second vehicle fueled and ready. Alternatively, landing systems might conduct emergency pickups, but that assumes landers are available and fueled. Every long-range mission needs contingency plans that don't rely on single-point solutions. The economic model for lunar mobility will evolve with base development. Early missions might use NASA-owned vehicles with limited capability. As commercial providers demonstrate reliable systems, the agency transitions to service contracts, paying per kilometer traveled or per mission completed rather than owning hardware. This approach worked for commercial cargo and crew services to the space station. It could work for lunar surface mobility if providers see sustainable business beyond NASA missions. What makes a vehicle commercial rather than government-owned? Risk transfer. Commercial providers invest their own capital in development, accepting the possibility of failure. They own and operate the hardware, selling capability rather than selling products. This model only works if there's a market beyond a single customer. On the Moon, that market might include private research missions, resource extraction operations, or tourism expeditions. Tourism seems distant when we're still planning the first permanent base. But mobility infrastructure built for NASA could serve other customers. A pressurized rover designed for science expeditions could host paying visitors wanting to experience lunar exploration. The economics change dramatically if vehicles support multiple revenue streams rather than depending solely on government contracts. International partners contribute mobility systems through the Artemis Accords framework. Japan is developing a pressurized rover as part of its contribution to the program. The vehicle incorporates Japanese robotics and life support technology while meeting NASA's operational requirements. This collaboration distributes development costs while bringing diverse technical approaches to common challenges. Mobility systems connect to broader base infrastructure through charging, communication, and servicing facilities. The base needs garage space for vehicle storage and maintenance. It needs charging stations with sufficient power capacity to replenish batteries between missions. It needs communication relays extending coverage beyond line of sight from base. Each capability requires its own infrastructure investment, planned and deployed in coordination with vehicle development. Autonomous operations become increasingly important as base complexity grows. Early missions might see crew manually driving rovers on every traverse. Later operations could use autonomous navigation for routine trips, positioning equipment, retrieving cached samples, conducting survey passes. Crew time is precious. Any task that automation can handle reliably frees astronauts for higher value activities. But autonomy on the Moon differs from Mars rover operations. Mars vehicles operate with 20-minute communication delays. They must make decisions independently because real-time control is impossible. Lunar operations allow near-instantaneous communication with Earth. Ground controllers can supervise autonomous systems, intervening when needed. This hybrid approach combines automation's efficiency with human oversight's flexibility. Machine learning could optimize traverse planning and obstacle avoidance. Rovers learn from experience which terrain types are safe to cross, which features indicate hidden hazards. Over multiple missions, vehicles build databases of local conditions that improve navigation efficiency. This works particularly well for unpressurized rovers conducting repeated traverses over familiar routes. The data these vehicles collect extends far beyond their primary transportation role. Every traverse generates terrain maps, composition data, radiation measurements. Rovers become mobile sensor platforms characterizing the lunar environment in detail. This information feeds back into base planning, identifying safe routes for future traverses, locating resources for extraction, mapping hazards that require mitigation. Mobility infrastructure scales with base expansion. Initial operations might use a single LTV supporting short-range sorties. As crew size grows and mission complexity increases, the base needs multiple vehicles, some dedicated to logistics, others to science, perhaps specialized units for construction or maintenance tasks. The pressurized rover might multiply into a fleet supporting simultaneous expeditions to different regions, but every vehicle adds operational overhead. Maintenance schedules, spare parts inventory, charging capacity, communication bandwidth. Each system requires resources. There's a balance between mobility capability and the infrastructure burden supporting it. Early base development might intentionally limit vehicle numbers to keep support requirements manageable, expanding the fleet only as infrastructure matures. This is how you extend human reach across the lunar surface, not through single heroic expeditions, but through systematic development of mobility systems integrated with broader base infrastructure. Vehicles that survive lunar conditions, carry the equipment science requires, keep crew safe during extended operations. Infrastructure that charges, maintains, and coordinates those vehicles as they execute missions far beyond what walking astronauts could achieve. The communication network tying all this together operates nothing like terrestrial systems. There's no atmosphere to carry radio waves efficiently, no satellites in convenient orbits providing continuous coverage. Line of sight becomes the dominant constraint. If you can't see it, you probably can't talk to it. Earth communication runs through direct links when the base is on the near side, visible from our planet. That provides high bandwidth connections for data transfer, video, mission control coordination. But lunar rotation creates blackout periods when the base passes to the far side. During those windows, communication routes through relay satellites or waits until Earth visibility returns. NASA's current architecture assumes direct Earth links handle most operations. The South Pole location helps. It remains visible from Earth more consistently than equatorial sites would. But there are still gaps. Future missions might deploy relay satellites in lunar orbit to close those coverage holes, particularly as operations extend beyond the immediate base vicinity. Local communication between base elements uses a mesh network. Habitat talks to power systems. rovers communicate their status. Instrument packages relay data. Each node in the network can route traffic, creating redundancy. If one path fails, data finds another route. This matters more than you might expect. Lunar dust, terrain features, equipment failures can all disrupt individual links. The pressurized rover serves as a mobile communication node during extended expeditions. As it travels beyond base range, it maintains contact with Earth directly or relays through base systems. This ensures crew never lose contact, even on multi-day traverses dozens of kilometers away. The rover's communication suite includes high-gain antennas for long-range links, omnidirectional antennas for local coordination, emergency beacons if primary systems fail. Data management becomes its own challenge. Science instruments generate massive data sets, high-resolution images, spectroscopy readings, seismic measurements, environmental sensors. All this information needs storage, processing, eventual transmission to Earth. Early missions might return physical storage devices with crews. Later operations require robust data infrastructure, servers, storage arrays, processing capability for preliminary analysis before transmission. Bandwidth limitations force prioritization. Which data gets transmitted immediately? What can wait for scheduled downlink windows? How much local processing occurs before transmission? These questions drive network architecture decisions. You don't want to discover critical findings sitting in a queue, because the system prioritized routine telemetry. Timing precision matters for science and safety. Seismic networks require synchronized timestamps across multiple sensors to triangulate moonquake sources. Navigation systems need accurate timing for position calculations. Coordinating operations between multiple vehicles or crew members demands everyone work from the same clock. On Earth, GPS satellites provide universal timing references. The Moon has no equivalent. Base systems likely use atomic clocks as timing sources, with synchronization protocols ensuring everything stays aligned. As the base grows, this timing infrastructure extends to remote sites, each major facility maintaining its own reference, periodically synchronized with the master clock. Network security operates differently than Earth systems, but remains essential. The base network controls life support, power distribution, habitat pressure, systems where unauthorized access could threaten crew safety. But the threat model differs from terrestrial networks. There's no internet connectivity, introducing random attack vectors. Access requires either physical presence or compromising specific communication links. Still, you need authentication and access control. Not every system should respond to every command source. Crew members might have different authorization levels. Automated systems need verification before executing critical operations. The architecture builds in these protections without creating operational bottlenecks. Security that maintains safety without impeding necessary work. Latency affects operations in subtle ways. Even at the speed of light, Earth-Moon communication takes about 2.5 seconds round trip. That delay makes real-time remote control impractical. Earth controllers can't drive rovers directly. Commands arrive too late to respond to immediate hazards. This drives the autonomy requirements discussed earlier. Systems must handle immediate situations locally, with Earth providing oversight rather than direct control. Video feeds experience similar constraints. Live video from the Moon arrives with that 2.5-second delay. For routine operations, that's acceptable. For emergencies requiring rapid response, local crew, and automated systems carry the burden. Mission Control sees what happened, not what's happening. They provide strategic guidance, not tactical, moment-to-moment direction. The network architecture must survive partial failures gracefully. If the main habitat loses power, backup systems keep communication active. If a dust storm damages antennas, redundant links maintain connectivity. If a rover loses contact, its autonomous systems execute safe protocols while it works to restore communication. This redundancy costs mass and complexity, but provides essential resilience. Expanding the base means extending the network. Each new habitat module needs integration. Additional rovers require coverage. Remote facilities demand connectivity. This growth must happen without disrupting existing operations. You can't take the network offline for upgrades when crew depend on it for survival. Modular design helps manage this expansion. Standardized interfaces allow new elements to connect without custom engineering each time. Protocols designed for scalability accommodate growing complexity. Automated configuration reduces the manual effort required to integrate new systems. The network grows organically as the base develops. Testing communication systems before crew arrival proves critical. Robotic missions establish initial infrastructure, verify coverage, validate protocols. These Pathfinder missions identify dead zones, test backup systems, confirm Earth visibility from proposed landing sites. By the time crew arrive, the communication foundation exists and functions as designed. But the lunar environment stresses equipment in unexpected ways. Temperature extremes crack solder joints. Radiation damages electronics over time. Lunar dust infiltrates connectors despite protective measures. Communication systems require maintenance schedules, spare parts inventory, procedures for field repair. Crew need training to diagnose and fix common failures. Upgrades arrive with each mission. New antenna designs, improved radio systems, enhanced data processing. Each increment adds capability without obsoleting existing infrastructure. Backward compatibility ensures new systems talk to old ones during transition periods. Over time, the network evolves from basic functionality to sophisticated capability. Autonomous systems rely on this network infrastructure. Robots conducting site preparation need command links. Drones surveying terrain require data transmission. Automated mining equipment coordinates through network connections. Each autonomous capability depends on reliable communication to operate safely and effectively. Human factors influence network design as well. Crew need intuitive interfaces for system monitoring and control. Voice communication requires clear audio quality despite equipment constraints. Video feeds need sufficient resolution for remote collaboration with Earth-based specialists. The network serves human needs, not just machine coordination. Emergency protocols define communication behavior during crises. If habitat pressure drops, the network prioritizes life support telemetry and crew communication. If power runs low, non-essential traffic gets suspended to conserve energy for critical systems. These protocols embed themselves in network management, activating automatically when conditions warrant. The base can't function without robust communication infrastructure. It connects distributed systems into coherent operations. It links lunar crew with Earth support. It enables the coordination and data flow that scientific exploration demands. Get the network right, and everything else has the foundation it needs to succeed. This digital nervous system grows more sophisticated over time. What starts as basic radio links evolves into a comprehensive information infrastructure supporting complex distributed lunar operations. Each mission adds capability. Each upgrade improves performance. Eventually, you have the communication backbone that sustained lunar presence requires. But communication is just information transfer. The base also needs physical resources, consumables that keep systems running and crew alive. Water, oxygen, propellant. On Earth, you order supplies. On the Moon, you manufacture them from local materials. That's where resource extraction transforms base operations from expensive to sustainable. Mining water ice from permanently shadowed craters transforms lunar economics. Lockheed Martin estimates each kilogram of water delivered from Earth costs around $100,000. Extract it locally, and that cost drops to essentially the energy required for excavation and processing. The Shackleton and de Gerlache craters near the South Pole contain billions of kilograms of water ice accumulated over millions of years. That's not just drinking water. It's rocket fuel, breathing air, and radiation shielding waiting to be harvested. The extraction process starts with prospecting. Rovers equipped with neutron spectrometers map hydrogen concentrations beneath the surface. Higher readings indicate ice deposits. Ground-penetrating radar reveals deposit depth and extent. This data guides excavation site selection. You want rich deposits near the surface in locations accessible to mining equipment. Excavation in permanently shadowed regions presents unique challenges. These craters never see sunlight. Temperatures hover around -230 degrees Celsius. Equipment must operate in darkness and extreme cold. Lighting systems provide visibility. Heating elements prevent mechanisms from freezing. Power cables snake from solar arrays on sunlit ridges down into the shadowed extraction zones. The mining itself resembles terrestrial operations, but adapted for lunar gravity and vacuum. Excavators scoop regolith containing ice. Conveyors transport material to processing facilities positioned at crater rims, where sunlight and Earth communications exist. You're essentially strip mining the crater floor, removing layers of ice-bearing soil systematically. Processing separates ice from regolith through several methods. Thermal extraction heats the soil, causing ice to sublimate directly from solid to vapor. Collection systems capture this vapor and condense it back to liquid water. Electrostatic separation uses electric fields to attract charged ice particles away from neutral regolith grains. Mechanical screening sieves out larger ice chunks that can be melted separately. The water yield varies dramatically depending on deposit concentration. Some regions contain 5% ice by mass. Others exceed 30% in particularly rich deposits. Processing efficiency determines how much usable water you extract per ton of regolith moved. Early systems might achieve 60% recovery. Mature operations could exceed 90% through refined techniques and recycled heat energy. But raw water is just the starting point. Electrolysis splits water molecules into hydrogen and oxygen. That oxygen becomes breathable air for habitats and rovers. The hydrogen combines with oxygen to create rocket propellant, essentially reversing the process that forms water. 1 ton of lunar water yields roughly 800 kilograms of oxygen and 100 kilograms of hydrogen when fully processed. Storage systems must handle multiple phases. Cryogenic tanks maintain liquid oxygen and hydrogen at extremely low temperatures. Pressurized containers hold gaseous oxygen for life support. Water remains liquid in heated tanks or freezes solid for long-term storage depending on immediate need versus future reserves. Each storage method serves specific purposes in base operations. The scale required for sustained operations is substantial. 4 crew members consume approximately 2 kilograms of oxygen daily for breathing. Add life support losses, airlock cycles, and contingency reserves, and you need roughly 3 tons of oxygen annually. That's processing about 4 tons of water or excavating perhaps 20 tons of regolith from a 20% ice concentration deposit. Manageable, but requiring continuous mining operations. Propellant production demands much larger quantities. A single human landing system needs roughly 100 tons of propellant for ascent from the lunar surface. Early missions bring their own fuel, but sustained operations require local production to avoid launching that mass from Earth. Producing 100 tons of propellant means processing 125 tons of water, which requires mining perhaps 600 tons of regolith. Now you're operating industrial-scale extraction facilities. Oxygen extraction from regolith offers an alternative path. Lunar soil is 40% oxygen by mass, locked in metal oxides and silicates. Break those chemical bonds, and you liberate oxygen without needing ice deposits. Several processes show promise. Molten regolith electrolysis melts soil and applies electric current to separate oxygen from metals. Hydrogen reduction uses imported hydrogen to chemically strip oxygen from regolith minerals. Carbothermal reduction employs carbon monoxide in high-temperature reactions that release oxygen gas. These processes produce metals as byproducts: iron, aluminum, titanium, silicon. Those materials enable construction beyond what Earth-supplied resources allow. Aluminum becomes structural elements. Iron reinforces habitats. Silicon creates solar panels and electronics substrates. Titanium offers lightweight strength for mechanical systems. What starts as oxygen production evolves into comprehensive materials processing. The energy requirements are enormous. Melting regolith demands temperatures around 1,600 degrees Celsius. Maintaining those temperatures continuously consumes megawatts of power. This is why nuclear reactors become essential for industrial-scale resource utilization. Solar arrays can't provide the continuous high power these processes require, especially during the 14-day lunar night. Automation reduces human labor in dangerous extraction zones. Teleoperated excavators work permanently shadowed craters without risking crew in darkness and cold. Autonomous haulers transport regolith to processing facilities without constant supervision. Robotic maintenance systems service equipment between human inspection visits. The mining operation runs largely unmanned, with crew providing oversight rather than direct operation. Quality control ensures purity standards. Extracted water must meet specifications for life support and propellant production. Contaminants like perchlorates or ammonia require removal through filtration and chemical treatment. Oxygen purity affects propulsion efficiency and crew health. Metal products need consistent composition for structural applications. Testing laboratories analyze samples continuously, adjusting processing parameters to maintain quality. Scaling production over time follows predictable patterns. Early missions extract just enough water for immediate crew needs and small-scale propellant demonstrations. As confidence grows, production ramps up to support propellant depots that refuel landing vehicles. Eventually, output reaches industrial levels, supporting not just the lunar base, but potentially Mars missions that refuel in lunar orbit using moon-derived propellant. Environmental impact monitoring tracks how extraction affects the lunar surface. Removing ice from permanently shadowed craters alters thermal properties and surface chemistry. Excavation creates dust that settles downrange from mining sites. Processing facilities vent exhaust gases that could contaminate pristine scientific sites. Responsible operations minimize these impacts through careful site selection and controlled processes. Economic models project return on investment. Initial infrastructure costs billions. Excavators, processors, storage facilities, power systems, transportation networks. But once operational, marginal production costs drop dramatically. Each additional ton of water costs only the energy and maintenance to extract it. Over decades, local resource utilization saves hundreds of billions compared to launching everything from Earth. Redundancy ensures production continues despite equipment failures. Multiple excavators mean one breakdown doesn't halt operations. Parallel processing lines allow maintenance without stopping extraction. Stockpiled reserves buffer against temporary production shortfalls. The system tolerates failures without threatening crew safety or mission timelines. Integration with base operations creates feedback loops. Life support systems consume oxygen produced from water or regolith. Propellant production enables frequent landing missions that deliver mining equipment upgrades. Metals extracted during oxygen production provide materials for expanding processing facilities. Each element reinforces the others in a self-sustaining industrial ecosystem. Waste management recovers resources from byproducts. Regolith tailings from water extraction still contain useful minerals. Slag from metal production provides radiation shielding material. Exhaust heat from processing warms nearby facilities. Nothing is truly waste when transportation costs make every kilogram precious. The transition from Earth-dependent to self-sufficient operations happens gradually. Early missions import most consumables. Middle phases produce oxygen and water locally while importing specialized chemicals and spare parts. Mature operations manufacture nearly everything on site, with Earth supplying only items impossible to produce with lunar resources. Advanced electronics, specialized pharmaceuticals, certain polymers. Expertise develops through hands-on experience. Early crews follow procedures developed on Earth, but they quickly discover local conditions require adaptations. Processing temperatures need adjustment for actual regolith composition. Excavation techniques evolve to handle unexpected soil properties. These lessons feed back to Earth, improving training for subsequent crews and refining equipment designs. Competition between extraction methods drives innovation. Multiple companies develop different approaches to water extraction and oxygen production. Performance data reveals which techniques work best in actual lunar conditions. Successful methods get adopted widely. Less effective approaches get abandoned or refined. Market forces optimize resource utilization without central planning dictating every technical choice. Safety protocols govern operations near extraction sites. Permanently shadowed craters are hazardous. Extreme cold, rough terrain, communication difficulties. Crew access requires special procedures. Buddy systems ensure no one works alone in these zones. Emergency shelters provide refuge if equipment fails. Rescue plans cover scenarios from injured personnel to stranded rovers. The psychological impact of successful resource utilization shouldn't be underestimated. Drinking water extracted from lunar ice and breathing oxygen split from lunar regolith makes the moon feel less alien, more like home. You're not just visiting, you're living off the land. That shift in mindset from explorer to settler changes how crew view their presence and purpose. Long-term sustainability requires closed-loop systems. Water recycling recovers moisture from crew respiration and hygiene. Carbon dioxide gets reduced back to oxygen and methane. Even solid waste undergoes processing to extract useful materials. The goal is minimizing imports by maximizing reuse and local production. Perfect closure remains impossible, but 95% efficiency makes the base vastly more sustainable than 50%. Technology transfer benefits Earth. Techniques developed for lunar resource extraction find applications in terrestrial mining, particularly in extreme environments like Arctic regions or deep underground. Water purification systems designed for lunar use improve desalination technology. Metal extraction processes reduce energy requirements in Earth-based industries. Lunar challenges drive innovations that ripple through the broader economy. International cooperation in resource utilization establishes precedents. The Artemis Accords include provisions for resource extraction and utilization rights. Countries contributing to mining infrastructure gain access to produced materials. Transparent accounting prevents disputes over resource allocation. These frameworks become templates for future space resource development on asteroids and Mars. But resource extraction is just converting local materials into useful products. The base also needs structures, habitats, workshops, storage facilities. Building those from lunar materials rather than importing them from Earth represents the next level of self-sufficiency. That's where construction technologies transform dust and rock into architecture. Constructing permanent structures from lunar regolith requires fundamentally different approaches than Earth-based building. You can't mix concrete, no water available in useful quantities initially. You can't weld steel beams, no oxygen-rich atmosphere for traditional metallurgy. The entire construction paradigm shifts from assembling imported materials to transforming local soil into functional architecture. Three primary technologies compete for dominance. Each has proven viable in testing. Each offers different advantages. Real lunar conditions will determine which becomes the standard. Laser sintering melts regolith directly. High-powered lasers sweep across the lunar surface, heating soil to 1,200 degrees Celsius. The material fuses into solid, ceramic-like structures as it cools. No binders needed, no imported materials required, just energy and dirt. ICON developed this approach as laser vitreous multi-material transformation. Their system uses concentrated solar power or nuclear-generated electricity to operate the lasers. A robotic gantry moves the laser head in programmed patterns, building up walls layer by layer. Each pass adds about 10 centimeters of thickness. The resulting material exceeds expectations. Compressive strength reaches 25 megapascals, stronger than many Earth concretes. The vitrified regolith resists radiation better than aluminum shielding. Temperature cycling from plus 120 to minus 170 Celsius doesn't crack it. Micrometeoroid impacts create surface pitting, but rarely penetrate. Construction speed depends entirely on available power. 1 megawatt of laser capacity produces about 100 square meters of wall per week. Modest, but adequate for initial facilities. Multiple laser systems working simultaneously accelerate the timeline significantly. polymer regolith composites offer different trade-offs. These mix lunar soil with specialized binders to create printable material. The regolith provides bulk and radiation shielding. Polymers supply tensile strength that pure sintered regolith lacks. Sidus Space and Kennedy Space Center developed a print head apparatus that extrudes these composites in simulated lunar vacuum. The system operates at -200 Celsius without degradation. Each extruded strand bonds to adjacent material, building up walls through accumulated layers. The challenge lies in polymer supply. Early missions must import these binders from Earth, but the mass requirements are surprisingly modest, only 5% of total structure mass. One cargo lander carrying polymers enables construction of multiple habitat modules using local regolith for the remaining 95%. Long-term sustainability demands polymer production from lunar resources. Carbon, hydrogen, and nitrogen exist in permanently shadowed craters. Extracting and synthesizing these into usable polymers requires complex processing equipment. But once established, the system eliminates Earth dependency for construction materials. Inflatable structures, wrapped in regolith shielding, combine imported and local materials creatively. A compact inflatable module ships from Earth, expanding to full size once deployed on the lunar surface. Then robotic systems pile regolith over the inflatable, creating radiation protection without complex manufacturing. This approach dominates early Artemis missions because it's simple and proven. The Foundation surface habitat uses exactly this design. A two-story inflatable element sitting atop a metallic base, both covered with meters of lunar soil for protection. But inflatable plus regolith isn't truly construction from local materials. You're still importing the primary structure. The regolith just adds shielding. For true self-sufficiency, you need methods that build entire facilities from lunar resources. Hybrid approaches combine techniques strategically. Foundation elements use sintered regolith for maximum strength and radiation protection. Upper stories employ polymer composites, where reduced mass matters more than shielding thickness. Transparent sections use sintered regolith glass, which forms when pure silicon-rich regolith melts and cools slowly. Different facility types favor different methods. Habitats need thick walls for radiation protection. Sintered regolith excels here. Workshops require interior flexibility for reconfiguration. Polymer composites allow easier modification. Storage bunkers just need volume and basic protection. Simple regolith berms suffice. The Foundation surface habitat demonstrates this thinking. Its metallic element provides critical systems and structure. The inflatable element offers living volume with minimal launch mass. Regolith shielding adds radiation protection using local materials. Future purely local material habitats will extend these principles further. Site preparation precedes actual construction. Robotic rovers level the building area, removing boulders and filling depressions. Excavation creates foundations below the surface, improving thermal stability and adding radiation protection from below. Compaction ensures the soil won't settle unevenly under structural loads. Precision matters more than you'd expect. Structures must connect to utilities, power cables, fluid lines, communications conduits. Misalignment by even 10 centimeters complicates connections. Autonomous construction systems use laser surveying to maintain tolerances within 2 centimeters across the entire building site. Modular design enables incremental expansion. The first habitat stands alone with full life support and power systems. A second habitat connects via printed regolith tunnel, sharing resources and providing redundancy. Third and fourth modules extend the complex. Eventually, you've got an interconnected base rather than isolated buildings. Dust management during construction prevents contamination. Sintering operations throw up plumes of fine particles. Polymer printing releases minor outgassing. Excavation kicks up abrasive regolith. Keeping this material away from seals, joints, and optical surfaces requires careful planning. Barriers of sintered regolith form dust control perimeters around active construction zones. Directional fans. Yes, fans work in vacuum when you're redirecting particles rather than moving air. Push disturbed material away from sensitive areas. Cleaning stations remove dust from equipment before it moves to clean zones. Interior finishing uses imported materials selectively. Wall panels cover raw regolith surfaces, providing mounting points for equipment and improving aesthetics. Flooring offers comfortable walking surfaces rather than rough sintered soil. Lighting, environmental controls, and communications infrastructure, installed just like in Earth buildings, adapted for lunar conditions. Quality control involves non-destructive testing. Ground-penetrating radar maps wall density, revealing voids or weak spots. Thermal imaging during construction shows temperature variations, indicating incomplete sintering. Structural load testing before habitation confirms each module meets safety standards. Repairs and modifications present unique challenges. You can't just knock out a wall and rebuild it. Sintered regolith doesn't reconnect reliably if you breach it and try to repair the gap. Planning must anticipate future needs. Routing conduits through walls during initial construction. Installing access panels, leaving expansion joints. Construction timelines depend on mission architecture. Early Artemis missions allocate minimal time to building, maybe 20% of surface EVA hours. As experience grows and robotic systems improve, construction consumes more crew time because it's enabling permanent presence rather than just supporting exploration. By Artemis 8 or 9, entire missions might focus on construction. Crew spends weeks operating robotic builders, troubleshooting systems, refining techniques. The goal shifts from visit the moon to build infrastructure supporting future missions. Automation handles most physical construction. Teleoperated systems build walls, while crew monitors from inside habitats. Autonomous robots perform repetitive tasks, layering material, checking dimensions, adjusting for irregularities. Human intervention focuses on quality assurance and handling unexpected situations. This human-robot teaming proves essential. Robots provide tireless precision. Humans offer problem-solving and adaptability. A jammed printhead needs troubleshooting. A laser misalignment requires diagnosis. Material inconsistencies demand adjusted parameters. Crew expertise keeps construction moving when automation encounters limits. Competition between contractors drives innovation faster than any single entity could achieve. Multiple companies develop their own construction technologies. NASA evaluates performance in actual lunar conditions. Successful approaches get licensed widely. Less effective methods improve or get abandoned. The construction market extends beyond NASA. Commercial lunar ventures need facilities too. Tourism companies want hotels. Mining operations require processing facilities. Research organizations need laboratories. This broader demand justifies private investment in construction technology development. Standardization emerges organically. Successful building techniques get copied and adapted. Interface specifications ensure modules from different manufacturers connect reliably. Safety requirements establish minimum performance criteria. The lunar construction industry develops its own best practices through accumulated experience. Material science advances through lunar construction. Engineers discover that certain regolith compositions sinter better than others. Some areas have soil that creates excellent polymer composites. Other regions have material better suited for bulk shielding. Geological surveys inform construction planning just like on Earth. The psychological impact of moving into locally built structures changes crew perspective. Living in a habitat that's fundamentally lunar, made from moon dirt, using moon resources, feels different than occupying imported equipment. You're not just visiting, you're building a permanent human presence. Training for construction operations starts on Earth. Mock-ups use lunar regolith simulant and vacuum chambers. Crew practice operating robotic systems under simulated delays, matching Moon-Earth communication lag. Troubleshooting exercises prepare them for equipment failures and material inconsistencies they'll face on site. But real lunar construction teaches lessons impossible to learn on Earth. Regolith behavior in 1/6 gravity differs subtly from simulations. Thermal cycling affects structures in ways Earth testing can't fully replicate. Each mission's construction activities generate knowledge that improves subsequent missions. Documentation becomes part of construction itself. High-resolution imaging captures every stage of building. Structural data feeds into engineering databases. Crew observations about what worked and what didn't inform technique refinement. This institutional knowledge accumulates into a genuine lunar construction manual. Safety margins in early construction are conservative, sometimes excessively so. Better to over-engineer and waste material than under-engineer and risk structural failure. As confidence grows from accumulated success, designs optimize toward efficiency without compromising safety. The first lunar building constructed entirely from local materials will mark a historic milestone. Not because it's technologically spectacular, the methods are relatively straightforward, but because it represents genuine self-sufficiency. Humans building permanent infrastructure using resources found on another world. That's fundamentally different from every previous space mission. Construction transforms the base from temporary outpost to permanent settlement. Imported habitats eventually wear out and get replaced by locally built structures. Expansion no longer depends entirely on Earth's supply chains. The Moon becomes not just a destination, but a place where humans build, live, and work using local resources. And once you've mastered construction, the base can grow to meet emerging needs, rather than being constrained by what fits in cargo landers. The timeline for all this extends across decades. NASA targets Artemis 5 for late 2028 as the first base building mission. But that's just groundbreaking, literally. The full base won't be complete for years beyond that initial start. Each subsequent mission adds capability. Artemis 6 might deliver the nuclear reactor components. Artemis 7 could bring additional habitat modules. Later missions expand infrastructure as needs become clear from actual operational experience. Scheduling depends on many factors beyond NASA's control. SLS production rates limit launch frequency initially. SpaceX must demonstrate Starship refueling works reliably. Blue Origin needs Blue Moon operational. Commercial lander providers have to deliver on their contracts. Political support matters enormously. $20 billion over 7 years sounds definite until you remember Congress appropriates money annually. Budget priorities shift. Administrations change. Sustained commitment across multiple election cycles isn't guaranteed. International partners add both capability and complexity. Italy's providing a habitat module through Thales Alenia Space. Japan contributes technology for the pressurized rover. Canada offers robotics expertise. Each partnership brings resources but also coordination requirements and potential delay points. The Artemis Accords framework shapes how this international collaboration functions. 61 countries have signed on, agreeing to principles for lunar activity. Transparency in operations, interoperability of systems, sharing of scientific data, emergency assistance protocols. These aren't legally binding treaties. They're multilateral agreements about norms and expectations, but they establish the governance framework for lunar base operations. When multiple nations have crew and equipment at Artemis Base Camp, clear protocols prevent conflicts and ensure cooperation. Commercial involvement transforms the economics. NASA isn't buying and owning every component. They're contracting services. Pay for delivery rather than purchasing landers. Lease rover usage instead of owning vehicles. This shifts development risk to companies while NASA focuses on mission objectives. 3 companies are developing the Lunar Terrain Vehicle: Intuitive Machines, Lunar Outpost, and Venturi Astrolab. They're competing for a service contract. NASA will evaluate their designs and pick the best performer. That company then operates the LTV as a commercial service available to NASA and potentially other customers. This commercial services model only works if there's a market beyond NASA. Tourism companies want lunar access. Mining ventures need surface infrastructure. Research institutions seek laboratory space. That broader demand justifies private investment that NASA couldn't fund alone. Standardization emerges through this commercial competition. Successful technologies get widely adopted. Interface specifications ensure equipment from different providers works together. Safety standards establish baseline requirements. The lunar economy develops its own industry practices, but there's tension between moving fast and building safely. Companies have incentive to demonstrate capability quickly to secure contracts. NASA has responsibility to ensure nothing fails catastrophically with crew on site. Balancing innovation speed against rigorous safety requirements creates constant negotiation. Testing happens in stages with increasing risk. Unmanned demonstrations prove basic functionality. Earth-based simulations validate operations under controlled conditions. Limited lunar trials test systems in actual environment. Only after extensive validation does crew-critical equipment get deployed. The Commercial Lunar Payload Services program began delivering robotic landers in 2024. These early missions carry scientific instruments and technology demonstrations. They're testing landing accuracy, payload integration, surface operations. Lessons learned feed directly into base construction planning. Some CLPS missions fail. That's expected with developmental programs. A lander might crash due to navigation error. Payload deployment could malfunction. Instruments might not survive the lunar night. Each failure provides data that improves subsequent attempts. This fail fast and learn approach works for robotic missions. Human missions require different standards. Crew can't be aboard experimental systems with uncertain reliability. So robotic precursor missions absorb the risk of unproven technology, while crewed missions use only thoroughly validated systems. The Foundation Surface Habitat represents NASA's most critical life support investment. It's the core structure where crew live during month-long stays. Two-story inflatable upper section provides living quarters. Single-story metallic lower section houses critical systems. Landing stage serves as foundation. Why inflatable? Mass efficiency. An inflatable structure packs compactly for launch, but expands to full volume on site. This provides more usable space per kilogram than rigid structures. Materials must resist micrometeorite impacts, provide radiation shielding, maintain pressure integrity, and handle thermal cycling. The habitat operates at 8.2 pounds per square inch with 34% oxygen, or 10.2 pounds per square inch with 26.5% oxygen depending on operational mode. These mixed gas atmospheres balance several factors. Pure oxygen at low pressure avoids decompression sickness but poses fire risks. Higher pressure nitrogen mixes reduce fire danger but complicate EVA preparation. The chosen atmospheres optimize this trade-off. Environmental control systems handle air revitalization, thermal regulation, humidity control, and contaminant removal. Life support processes water from multiple sources, condensate from humidity, urine through processing systems, and imported reserves. CO2 gets reduced back to oxygen through chemical processes. High-pressure oxygen generation supports both habitat atmosphere and rover resupply. Waste management extends beyond simple trash handling. Biological waste requires processing to prevent contamination. Packaging materials need compaction for efficient storage. Some waste might get recycled into useful materials through pyrolysis or chemical breakdown. Establishing a waste management system that handles all waste streams with minimal earth resupply is complex engineering. The habitat serves multiple functions beyond living quarters. It's the communications hub, linking surface operations with Earth and with orbiting spacecraft. It's a science facility where crew analyze samples and conduct experiments. It's the EVA equipment maintenance workshop where spacesuits get serviced. It's the supply depot storing consumables and spare parts. This multifunctionality means systems must not interfere with each other. Communication equipment can't generate electromagnetic noise that disrupts scientific instruments. Maintenance activities can't contaminate clean room areas where samples get studied. Spatial organization within the habitat becomes critical design consideration. The Italian multipurpose habitation module adds capability in later missions. It operates autonomously when crew aren't present, performing automated research or monitoring base systems. It can relocate on the surface, which suggests some mobility system, possibly wheels or skids for short-distance moves to connect with other structures. This mobility feature enables base expansion without launching entirely new structures. Early modules land at dispersed locations as landing accuracy improves. Later, those modules move into connected configuration. The base grows organically from separated components into integrated complex. Power infrastructure undergoes similar evolution. Initial missions rely on solar arrays positioned to catch continuous sunlight on the crater rim. These provide baseline power during illuminated periods. Battery banks store energy for shadow transits lasting up to 8 days, based on specific site geometry. The nuclear fission reactor fundamentally changes operational capability. A 100 kilowatt reactor provides continuous power regardless of sun angle or lunar night. That's enough for all habitat systems, rover charging, construction equipment, water processing, oxygen generation, and scientific instruments with reserve capacity for future expansion. Reactor design must meet stringent constraints. Under 6 metric tons total mass, including power conversion, heat rejection, and distribution systems. Operates reliably for at least 10 years without maintenance requiring specialized facilities. Handles lunar thermal extremes and radiation environment. Fails safely if any component malfunctions. Heat rejection poses interesting challenges. On Earth, air or water cooling dissipates reactor heat. The Moon has neither. Radiators must reject heat directly to space through thermal radiation. In vacuum, this requires large surface area operating at high temperature. Those radiators become prominent base features. Placing the reactor requires careful site selection. It should be distant enough from habitats that any malfunction doesn't endanger crew, but close enough that power transmission losses stay minimal. Shielding reduces radiation exposure to safe levels at habitable areas. Terrain features might provide natural shielding, putting the reactor behind a crater rim relative to the habitat, for instance. The landing pad construction demonstrates ISRU at architectural scale. You need a prepared surface for landers to touch down without kicking up regolith that damages nearby equipment. Simply clearing and compacting dirt provides basic functionality. Sintering or paving creates more durable surface. Laser sintering fuses regolith particles into solid ceramic-like material. Robotic systems traverse the landing zone, melting soil layer by layer. The result resembles glazed pottery, hard, relatively smooth, resistant to erosion from rocket exhaust. It's not perfectly smooth like concrete, but adequate for lander legs. Polymer regolith composite offers alternative approach. Mix lunar dirt with polymer binder. Lay it down in controlled layers. Compact and cure. This creates surface that's somewhat flexible rather than brittle ceramic. Different mechanical properties might better handle repeated lander impacts and thermal cycling. Which method works better isn't certain until both get tested extensively in actual lunar conditions. Earth-based simulations use lunar regolith simulant and vacuum chambers, but subtle differences between simulant and real regolith affect results. Some lunar soil regions might work better with sintering, others with composite paving. The first landing pad will likely be over-engineered, built more robust than strictly necessary, because uncertainty about long-term performance demands conservative design. Later pads incorporate lessons learned and optimize toward efficiency. Radiation shielding improves as construction capability matures. Initial habitats include integrated shielding in their structure, plus local regolith piled around vulnerable sections. Purpose-built radiation shelters offer high protection zones where crews shelter during solar particle events. Long-term shielding might involve excavating into crater walls and building partially buried structures. Meters of regolith overhead block most radiation. Temperature stability improves underground. Micrometeorite risk drops essentially to zero. The engineering challenge lies in excavation, structural support, and waterproofing against any subsurface ice that might sublimate. Psychological aspects of living underground matter too. Humans tolerate enclosed spaces better with windows or screens showing outside views. Lighting design affects mood and circadian rhythms. Spatial layout influences social dynamics among crew. The habitat isn't just life support engineering, it's architecture shaping human experience. As the base expands, distinct functional zones emerge. Habitation areas separate from industrial zones where noisy or dirty operations occur. Scientific facilities need clean environments isolated from contamination. Storage areas concentrate near landing zones for efficient cargo handling. The base develops urban planning at miniature scale. Transportation networks connect these zones. Pressurized tunnels might link habitats, so crew move between structures without suiting up. Roads for rovers radiate from the central area toward exploration sites and resource extraction locations. Eventually, you have infrastructure layout resembling a small town. Not just scattered buildings, but organized settlement. This organization isn't planned completely in advance. Early missions establish core facilities based on projected needs. Actual operations reveal inefficiencies and opportunities. Subsequent missions adjust layout based on lessons learned. The base plan evolves through iterative refinement rather than executing a fixed master blueprint. That adaptability distinguishes Artemis from Apollo. Apollo missions followed predetermined plans with minimal deviation. Artemis treats the base as a living project that responds to discoveries, technological developments, and changing objectives. Flexibility enables long-term success where rigid planning would fail. The vision extends beyond Artemis Base Camp itself. Lunar infrastructure supports Mars preparation. Long-duration habitation tests life support systems for Mars missions. ISRU techniques developed on the Moon apply to Martian regolith. Radiation shielding strategies inform Mars habitat design. The Moon becomes a proving ground for deep space exploration. Commercial lunar economy grows alongside NASA operations. Private companies establish their own facilities near Artemis Base Camp, sharing some infrastructure while maintaining independent capabilities. Tourism ventures bring paying visitors. Mining operations extract valuable materials. Research stations conduct science NASA doesn't prioritize. This mixed government-commercial presence transforms the lunar surface from exclusively national territory to economically productive zone. The Artemis Accords provide governance framework, but market forces increasingly drive activity. NASA remains anchor tenant, but not sole operator. Decades from now, Artemis Base Camp might be one of several lunar settlements. Different nations or coalitions establish their own bases at scientifically interesting locations. Commercial spaceports support private spacecraft. Industrial facilities process lunar resources into exportable products. The Moon becomes multipolar rather than dominated by a single program, but that future depends on success at each incremental step. The first habitat must work reliably. The first reactor must provide stable power. The first locally constructed building must prove ISRU viability. Each milestone builds confidence and capability for the next advance. Artemis isn't just building a base, it's establishing humanity as multiplanetary species, not through dramatic leap to Mars, but through patient development of technologies and operational expertise needed for permanent off-Earth presence. The Moon is close enough to learn those lessons without catastrophic risk, distant enough to force genuine self-sufficiency. That's why Artemis matters beyond flags and footprints. It's infrastructure enabling everything that comes after. When humans eventually walk on Mars, they'll use life support systems proven at Artemis Base Camp. When asteroid mining becomes economically viable, it'll build on ISRU techniques developed on the Moon. When permanent space settlements exist, they'll trace their heritage to lessons learned in lunar regolith. The base is beginning. What it becomes depends on countless decisions, innovations, and commitments across coming decades. But the foundation is being laid right now, starting with Artemis 5 in 2028. Every component delivered, every system tested, every structure built moves humanity closer to permanent presence beyond Earth. The Moon isn't the destination, it's the doorway. The base NASA's building isn't just another space station. It's humanity learning to live somewhere that's actively trying to kill us every second, and doing it 400,000 kilometers from the nearest hardware store. Think about what this represents. In 2028, the first permanent structure starts rising from lunar regolith at the South Pole. By the mid-2030s, crews might spend 2 months at a time living in habitats built partly from moon dirt, breathing oxygen extracted from that same dirt, drinking water mined from ancient ice deposits that have sat frozen in shadowed craters for billions of years. That's not exploration in the Apollo sense, that's settlement. The Artemis program is engineering every system, power, life support, mobility, construction, resource extraction, to function independently of Earth's supply lines, not completely independent initially, but moving steadily towards self-sufficiency that makes sustained presence possible rather than ruinously expensive. Nuclear reactors providing 100 kilowatts continuously, water extraction processing tons of ice annually, construction robots sintering regolith into radiation shielding walls, rovers that let crews explore hundreds of kilometers from base, all of it working together as integrated infrastructure rather than disconnected experiments. The timeline stretches across decades because you can't build a permanent base in a handful of missions. Each landing adds capability. Each crew rotation advances construction. The base grows incrementally from initial foothold to genuine settlement. But here's what makes this different from every previous space program: the commercial involvement. NASA isn't building and owning everything. They're contracting services from companies that see markets beyond government missions. That fundamentally changes the economics and sustainability. When Intuitive Machines or Lunar Outpost operates rovers as commercial services, they're incentivized to make those systems reliable and cost-effective because their business depends on it. When Blue Origin and SpaceX develop landers, they'll reuse across multiple missions. They absorb development risk while driving down marginal costs. When construction companies perfect regolith sintering, they can sell that capability to mining ventures and tourism operators. The Artemis Base Camp becomes anchor tenant in broader lunar economy rather than isolated government outpost. That's how you achieve sustained presence, by making the Moon economically productive, not just scientifically interesting. International collaboration through the Artemis Accords adds resilience too. 61 countries participating means the program isn't dependent on any single nation's political cycles. Italy provides habitat modules. Japan contributes rover technology. Canada offers robotics expertise. The base becomes truly multinational infrastructure, and every technology developed for lunar operations has applications beyond the Moon. Water extraction techniques improve terrestrial desalination. Radiation shielding advances nuclear safety on Earth. Regolith construction methods work in extreme terrestrial environments. ISRU principles apply to Mars, asteroids, anywhere humans might venture. The base is testing ground for everything deep space exploration requires. Life support systems running for months without resupply. Radiation protection for crew beyond Earth's magnetic field. Resource extraction making local materials into useful products. Construction methods building permanent structures from native materials. Mars missions will use life support proven at Artemis Base Camp. Asteroid mining will build on ISRU techniques developed on the Moon. Permanent space settlements will incorporate lessons learned from lunar operations. The base isn't the destination, it's the foundation for everything beyond. But none of this happens without solving problems we've never faced before. Operating nuclear reactors on the Moon. Building structures from dirt using lasers. Mining water from permanently shadowed craters at -230 degrees Celsius. Keeping humans alive for months in an environment with no air, no water, temperature swings of 300 degrees, and radiation that would kill them without protection. The engineering required pushes every discipline to its limits. Materials, science creating polymers that function in lunar vacuum. Power systems generating electricity through 14-day nights. Construction robotics building autonomously with minimal human supervision. Life support recycling everything to 95% efficiency. And it all has to work reliably, because crew can't just hop on a rocket home if something breaks. The nearest help is 3 days away at best. Systems need redundancy, spare parts, repair procedures crew can execute with available tools. Failure tolerance has to be engineered into everything. That's why the timeline is measured in decades, not years. You don't rush infrastructure that people's lives depend on. You test exhaustively. You validate through unmanned missions. You build incrementally, proving each system before adding the next. The first crew moving into a habitat constructed entirely from lunar materials. That's the milestone that changes everything. Not because the technology is spectacular, but because it proves humans can build permanent structures on another world using local resources. At that point, expansion is limited by capability and will, not by what fits in cargo landers. The base transforms from temporary outpost to permanent settlement. Imported habitats eventually wear out and get replaced with locally built structures. Construction scales to meet needs rather than being constrained by Earth's supply chains. The Moon stops being a destination and becomes a place where humans live and work. That's the future Artemis is building toward. Not dramatic flags and footprints moments, but patient infrastructure development enabling sustained presence. The kind of presence that lets scientists conduct years-long experiments, that lets engineers refine resource extraction to industrial scale, that lets construction crews build facilities we haven't even imagined yet. 50 years from now, Artemis Base Camp might be one of several lunar settlements, different nations operating their own bases, commercial ventures mining valuable materials, tourism companies hosting visitors, research stations conducting science impossible on Earth. The Moon becomes multiplanetary human civilization's first step beyond Earth. But that future depends entirely on what happens in the next decade. The first habitat must function reliably. The first reactor must provide stable power. The first locally constructed building must prove ISRU works at architectural scale. Each success builds confidence and capability for the next advance. This is how humanity becomes multiplanetary. Not through science fiction magic, but through systematic engineering solving practical problems. Making water from ice, making oxygen from dirt, making shelter from regolith, making permanent presence possible through accumulated capability rather than heroic one-shot missions. The Moon is close enough to develop these capabilities without catastrophic risk if something goes wrong. It's distant enough to force genuine self-sufficiency rather than depending on constant Earth support. It's the perfect proving ground for everything deep space exploration requires. When humans walk on Mars, they'll use systems proven on the Moon. When asteroid mining becomes reality, it'll build on lunar resource extraction experience. When permanent space settlements exist, they'll trace their lineage directly to Artemis Base Camp. The base isn't just about the Moon. It's humanity learning to live beyond Earth, learning to extract resources from alien environments, learning to build from local materials, learning to maintain complex systems without Earth's industrial base backing you up. Every lesson learned at Artemis Base Camp applies everywhere humans might go. The Moon is just the beginning. NASA's spending $20 billion to establish that beginning. To put the first permanent human foothold on another world. To prove we cannot just visit space, but live there. And it all starts in 2028 with Artemis 5, when construction equipment lands at the South Pole and crews begin transforming lunar regolith into the foundation of humanity's first extraterrestrial settlement. Everything we've talked about, the habitats, the power systems, the rovers, the resource extraction, the construction technologies, it's all real hardware being developed right now, tested in vacuum chambers, validated in lunar simulant, prepared for actual deployment. The Artemis Base Camp will be humanity's first permanent presence beyond Earth. The place where we learn to live on another world. The foundation for everything that comes after. That's not science fiction. That's the next decade of space exploration. And it's just the start.